In Chapter 10, we will continue our hypothesis testing, this time looking at hypothesis testing for two samples. In this chapter, we will learn how to perform hypothesis tests for two samples for independent means, for dependent means, and for proportions. This chapter builds on our knowledge from the previous chapter, allowing us to compare two populations or two samples to each other. First, if we have two independent means and the population standard deviation is known for both of them, we will be using the normal distribution using the two-sample z-test. When the population standard deviation is not known for both of them, we will use the student t-distribution using the two-sample t-test. If we have two independent proportions, we will use the normal distribution and we will use the two-proportion z-test. If we have two dependent means, we will use the student t-distribution and we will be doing a t-test. Now, writing the hypotheses will look fairly similar, but there are some differences. The biggest difference is hypotheses no longer compare a population parameter to a proposed value, but rather compare two population parameters. These are the possibilities. Notice all of the pairing of symbols is still the same. We've got three possibilities for if we're talking about means, three possibilities for if we're talking about proportions. Now these are all for independent samples. Later on at the end of the chapter, we will talk about how we handle dependent means. So if we have two independent populations with a known population standard deviation for each of them, we will be doing a two-sample z-test. Now this is our formula for z, and we notice that things are starting to get a little bit messier, so it'll probably be good to lean on our calculators. On your calculator, you can go to Stat, over to Tests, and you'll find two-samp z-test, two-samp t-test, two-prop z-test, and those will be the ones you'll be using for your independent populations. Let's talk about our hypothesis testing steps. It's the same 5 steps that we've seen before. State your hypotheses, identify your claim, state the level of significance, and your critical value if you're doing the traditional method. Find your test statistic and the p-value if you're doing the p-value method, which if you're using the calculator, most of you are. You'll then make a decision, reject or not reject the null hypothesis, and then write your conclusion sentence. Remember, only use the word not in your sentence if you decide do not reject the null hypothesis. You use the word support if the alternative hypothesis is the claim, and you use the word reject if the null hypothesis is your claim. You can always refer back to the table I gave you last chapter when writing your sentence. Let's look at an example. A custodian wishes to compare two competing floor waxes to decide if one is best. He believes the mean of wax win is greater than the mean of wax co. In a random sample of 50 floors of wax win and 52 of wax co, wax win had a mean lifetime of 24.1 and wax co had a mean lifetime of 23.8. The population standard deviation for wax win is assumed to be 9.3, and the population standard deviation for wax co is assumed to be 5.6. Perform a hypothesis test using a level of significance of 0.01 to help him decide. First, we want to write our hypotheses. Comparing wax win to wax co, we're claiming that wax win has a greater mean than wax co. So our null hypothesis would be that the mean of wax win is less than or equal to the mean of wax co. The alternative hypothesis, which is our claim, is that the mean of wax win is greater than the mean of wax co. In step 2, we list our level of significance and our critical value. Then we can draw things into a picture again if we desire. We then want to find our test value and p-value. Using our calculator, performing the 2SAMP-Z test, we find that z equals 0.196 and p equals 0.422. So from this, we see that z is not in the tail area, and we see that alpha is not greater than p, so we're able to make the decision, do not reject the null hypothesis. Thus, our sentence will state there is not enough evidence to support the claim that Waxwin lasts longer than Waxco. A custodian wishes to compare two competing floor waxes to decide which one is best. He believes the mean of Waxwin is greater than the mean of Waxco. In a random sample of 33 floors of Waxwin and 30 of Waxco, Waxwin had a mean lifetime of 26.6 and Waxco had a mean lifetime of 27.3. The population standard deviation for Waxwin is assumed to be 6.1 and the population standard deviation for Waxco is assumed to be 5.3. Perform a hypothesis test using a significance level of 0.1 to help him decide. Our claim here is the alternative hypothesis. The null hypothesis has a less than or equal to symbol, and the alternative has a greater than symbol, stating that the mean of Waxwin is greater than the mean of Waxco. Our level of significance is 0.1, and our critical value is 1.28. Using the 2SAMP-Z test on our calculator, we would find that z is negative 0.487 and p is 0.687. So in step 4, we can make the decision, do not reject the null hypothesis. And step 5, there is not enough evidence to support the claim that Waxwin lasts longer than Waxco. Now, if we have two independent populations with unknown population standard deviation, and we are testing means, we will use the two-sample t-test. On our calculator, this is abbreviated as 2SAMP t-test. And as you can see from the formula here, it might be best to go ahead and lean on our calculators. In our example, we see a researcher is interested in seeing if the average income of rural families is greater than that of urban families. To see if his claim is correct, he randomly selects 20 families from a rural area and finds that they have an average income of $66,045 with a standard deviation of $803. He then selects 20 families from an urban area and finds that they have an average income of $65,455 with a standard deviation of $927. Perform a hypothesis test using a significance level of 0.01 to help him decide. So we state our hypotheses. In our null hypothesis, we have a less than or equal to symbol, and in our alternative hypothesis, we have a greater than symbol, stating that the mean of rural families is greater than the mean of urban families. The alternative hypothesis is our claim. In step 2, we're stating our level of significance and identifying our critical value. And then in step 3, we're finding our test value and our p-value. We can either find our test value by the formula or by using the 2SAMP t-test on our calculator. The 2SAMP t-test does also give us the p-value. So we have a t-value of 2.151 and a p-value of 0.019. This leads us to the decision, do not reject the null hypothesis. So our conclusion statement is, there is not enough evidence to support the claim that rural families have a higher average income than urban families. A researcher is interested in seeing if the average income for rural families is less than that of urban families. To see if his claim is correct, he randomly selects 16 families from a rural area and finds that they have an average income of $96,045 with a standard deviation of $935. He then selects 10 families from an urban area and finds that they have an average income of $69,967 with a standard deviation of $822. Perform a hypothesis test using a significance level of 0.01 to help him decide. We would state our hypotheses in our first step, and we identify our claim as the alternative hypothesis. Then in step 2, we're stating our level of significance and identifying our critical value. Then we find our t-value and p-value. We find these by using the 2-SAMP t-test on our calculator. If we were to draw a picture, we would see that our t-value is in the tail area. We also can compare alpha and p, and we see that alpha is greater than p. This leads us to the decision, reject the null hypothesis. Thus, we are able to say there is enough evidence to support the claim that rural families have a lower average income than that of urban families. Now let's talk about two independent proportions. We would be using the two-proportion z-test, or as your calculator often will abbreviate it, 2-prop z-test. The formula has again gotten a bit messy. Some notation here. P sub t is equal to x sub 1 plus x sub 2 divided by n sub 1 plus n sub 2. A student pursuing a degree in English as a second language believes the proportion of female factory workers who can't speak English is less than the proportion of male factory workers who can't speak English. To test her claim, she randomly selects 300 female factory workers, and out of them, 47 could not speak English. She then randomly selects 324 male factory workers, and out of them, 67 could not speak English. Test her claim at alpha equals 0.05 to see if she was right. We would set up our hypotheses. This time we're using proportions instead of means, so we have p's instead of mu's. Our null hypothesis would have a greater than or equal to symbol, and our alternative hypothesis has a less than symbol, saying that the proportion of females is less than the proportion of males. This alternative hypothesis is our claim. We then state our level of significance and identify our critical value. We then can compute our test value and our p-value. Our test value is negative 1.619, and our p-value is 0.0527. We see that our test value is not in the tail area, and our p-value is just a little bit bigger than our alpha. This tells us we do not reject the null hypothesis. So we can state there is not enough evidence to support the claim that the proportion of female factory workers who cannot speak English is smaller than the proportion of male factory workers who cannot speak English. A student pursuing a degree in English as a second language believes the proportion of female factory workers who can't speak English is greater than the proportion of male factory workers who can't speak English. To test her claim, she randomly selects 201 female factory workers, and out of them, 69 could not speak English. She then randomly selects 271 male factory workers, and out of them, 60 could not speak English. Test her claim at alpha equals 0.05 to see if she was right. So you would write your hypotheses and identify the null hypothesis as being the proportion of females being less than or equal to the proportion of males. And the alternative hypothesis, which is your claim, the proportion of females is greater than the proportion of males. Your level of significance alpha is 0.05, and your critical value is 1.28. You would then calculate Z and P. You find that Z is 2.938, and your P is 0.002. From this, you can reject the null hypothesis, so you're able to say that there is enough evidence to support the claim that the proportion of female workers who cannot speak English is larger than the proportion of male factory workers who cannot speak English. Now let's talk about having dependent populations, specifically talking about means. When two populations are dependent, instead of comparing the difference of the means, we will compare the mean of the differences. So instead of having an inequality with the mean on each side, we're going to find the difference of our data values and then find the mean of those differences. We're going to compare that mean of the differences to 0. So these are the possibilities for our hypotheses. We will be using the t-test as we perform these tests. The t-test is the same test that we used last chapter when we had to use the student t-distribution. Let's look at an example together. A researcher wishes to test the effects of exercise on the ability to complete a basic skills test. He designs a pre-test and a post-test to give each participant. You believed that there would be improvement in this course. You believe that the population of the differences is approximately normally distributed, but you do not know the population standard deviation. Test your belief with a 0.05 level of significance. In order to perform this test, we need to find the differences. Let's do post-test minus pre-test and find the differences between these scores. Each row is representing one student. So each student is given a pre-test and given a post-test, and we're keeping these scores paired together. We sometimes call this paired data or a paired test. So doing post-test minus pre-test, we end up with 0, 10, -7, 2, 0, -4, 7, 7, -3, -6, -1, -4, -6, 0, 2, 7, 5, and 7. Now, if post-test minus pre-test is positive, that would mean that there was improvement. So that helps us write our hypotheses. So the null hypothesis would be the mean of the differences less than or equal to 0. The alternative hypothesis, the mean of the differences is greater than 0. The difference is positive, meaning an improvement here. So the alternative hypothesis is our claim. Now our level of significance is 0.05, and our critical value is 1.740. So now let's find our test value. We can type this list of data values into our calculator and then perform a t-test. We would find a t-value of 0.711 and a p-value of 0.243. We would then say that we do not reject the null hypothesis, and there is not enough evidence to support the claim that there was improvement in the scores. A researcher wishes to test the effects of exercise on the ability to complete a basic skills test. He designs a pre-test and a post-test to give each participant. You believed that there would be a difference in the scores. Test your claim at a 0.05 level of significance. We want to do post-test minus pre-test, keeping in mind that if post-test minus pre-test is positive, there would be improvement. So the hypotheses are that the mean of the differences equals 0 for the null hypothesis, and the mean of the differences is not equal to 0 for the alternative hypothesis. The alternative hypothesis is the claim. This is a two-tailed test, so our critical values are positive and negative 1.761. Our level of significance was 0.05. Using the t-test on the calculator, entering the data into the list, we find that the t-value is equal to 0.957 and the p-value is equal to 0.355. This leads us to the decision: do not reject the null hypothesis. So there's not enough evidence to support the claim that there was a difference in the scores.